40 light-years away, in the constellation Aquarius, there is a small red star orbited by 7 rocky, Earth-sized planets, 3 of them sitting squarely inside its habitable zone. When astronomers found this system in 2017, it was treated as one of the most important discoveries in the history of the search for life beyond Earth, a genuine laboratory for testing whether worlds like our own could exist somewhere else. Ever since the James Webb Space Telescope came online, this exact system has been one of its highest priority targets, planet after planet, transit after transit, all working toward a single question. And piece by piece, planet by planet, the answer Webb keeps sending back is not the one anyone in the exoplanet community was hoping for. Tonight, we're looking at what James Webb has actually found in the TRAPPIST-1 system, why the results have been quietly disappointing astronomers for 2 straight years, and why this particular finding matters for far more than just 7 planets around one small star. To understand why the system matters so much, you have to understand what made it special in the first place. TRAPPIST-1 was revealed in 2017 using data from NASA's now-retired Spitzer Space Telescope combined with ground-based observatories as the record holder for the most Earth-sized rocky planets ever found orbiting a single star. All 7 of its planets are comparable in size to Earth. All 7 transit their star from our point of view, meaning every single one of them can, in principle, have its atmosphere. Studied directly using transmission and thermal emission spectroscopy, the same basic technique astronomers have used to study other distant worlds. And because the TRAPPIST-1 is a red dwarf, the single most common type of star in the entire galaxy, understanding whether planets around it can hold onto real atmospheres has implications reaching far beyond this one system. If red, dwarf planets can be habitable. The number of potentially livable worlds across the Milky Way explodes. If they can't, an enormous fraction of the galaxy's planets may be effectively ruled out before we ever get the chance to study them closely. That's what made TRAPPIST-1 such an obvious priority the moment Webb came online. 7 planets, all transiting, all roughly Earth-sized, sitting close enough at 40 light-years to be genuinely studied in detail rather than merely detected. No other known system offers this particular combination. This many rocky, temperate zone-adjacent worlds bundled around a single star, all conveniently lined up for repeated observation. Astronomers didn't just want to check whether this system had habitable planets. They wanted to use it as a template, a controlled experiment testing whether the most common stars in the galaxy could realistically host the kind of atmospheres life depends on at all. Webb began testing that question almost immediately after starting science operations, and the results started coming in fast. The first target was TRAPPIST-1b, the innermost planet in the system, sitting closest to its star and therefore expected to be the least likely candidate for holding onto an atmosphere. In 2023, a team led by Thomas Green performed the first thermal emission measurement ever taken of a planet this small and this cool, a genuine technical milestone, on its own. The result? No evidence of a significant atmosphere. The planet's measured temperature matched what you'd expect from a bare, airless rock, with nothing insulating or redistributing heat around its surface the way a real atmosphere would. A separate team led by Sebastian Ziba reached essentially the same conclusion studying TRAPPIST-1c, the second planet from the star, finding no evidence of a thick atmosphere there either. Those first 2 results were disappointing, but not entirely surprising. Planets B and C sit so close to their star that intense radiation was always expected to make survival difficult for any atmosphere. What made the picture genuinely concerning was what came next. In April of 2026, a team led by Michael Gillen, the same astronomer who helped discover the TRAPPIST-1 system in the first place, published a more rigorous follow-up study in the journal Nature Astronomy, using an observational method called thermal phase curves, tracking how each planet's temperature changes continuously as it orbits its star, rather than relying on a single snapshot measurement. The confirmation was unambiguous. Neither TRAPPIST-1b nor TRAPPIST-1c shows any sign of a thick atmosphere. The bare rock scenario wasn't a fluke of the initial measurement. It held up under a completely independent, more thorough method of testing. Then came the planet that mattered most. TRAPPIST-1d sits right at the inner edge of the system's habitable zone, similar in size to Earth, rocky, and positioned at a distance from its star where liquid water could theoretically exist on its surface if the right atmospheric conditions were present. It was on paper one of the most promising individual targets in the entire search for potentially habitable worlds beyond our solar system. In January of 2026, a team led by Caroline Piole-Goriev of the University of Chicago and the Trottier Institute for Research on Exoplanets published their findings using Webb data specifically, targeting this planet. Their conclusion, stated plainly in NASA's own release of the results, TRAPPIST-1d does not have an Earth-like atmosphere. As Piole-Goriev put it directly, while the team didn't find a big, bold atmospheric signature at planet D. This specific candidate could now be ruled out from the shortlist of potential Earth twins. It's worth pausing on how significant that particular result felt within the field. Of the 7 TRAPPIST-1 planets, D was widely regarded as one of the 2 or 3 most likely candidates to actually resemble something habitable, sitting precisely where theoretical models predicted the best odds of liquid water existing on a solid surface. Losing that specific candidate wasn't just one data point among many. It removed one of the system's strongest individual selling points, the kind of planet popular science coverage had spent years describing as a genuine contender for an Earth twin. Ryan McDonald, a co-author on the study, was careful to note that all hope wasn't necessarily lost for the more distant planets in the system, planets E, F, G, and H, which sit further from the star's most intense radiation and colder environment, even as he acknowledged that TRAPPIST-1d itself may simply be a barren rock illuminated by an unforgiving red star. That's 3 planets in a row, all showing the same pattern. And the 4th data point, while slightly more ambiguous, didn't exactly bring relief either. TRAPPIST-1e, often considered the single most promising planet in the entire system because of its size and position, was studied by a team led by Anna Glidden at MIT, with results published in September 2025 across a series of papers in the Astrophysical Journal Letters. The findings there were genuinely mixed. The team was able to rule out a thick, Venus-like or hydrogen-rich atmosphere on the planet, narrowing the possibilities considerably, but the data couldn't fully distinguish between a thin, nitrogen-based atmosphere similar to Titan's, complete with traces of methane, or the possibility of no atmosphere at all, stellar. Flares and star spots from TRAPPIST-1's own active turbulent surface kept contaminating the signal, making a clean answer frustratingly difficult to pin down even with Webb's exceptional sensitivity. Put these 4 results together, and a pattern starts to emerge that nobody working on this system particularly wanted to see. Of the 4 TRAPPIST-1 planets studied in detail so far, 3 show no evidence of any meaningful atmosphere at all, and the 4th remains genuinely uncertain, with the most optimistic scenario being a thin, hazy atmosphere rather than anything resembling Earth's. The single most promising nearby laboratory for testing whether rocky planets around red dwarf stars can support the kind of atmosphere life depends on so far, returning results that lean heavily toward disappointing. The likely explanation traces back to the nature of the star itself. Red dwarfs like TRAPPIST-1 are far cooler and fainter than stars like our own Sun, which means any planet sitting in their habitable zone has to orbit extremely close to actually receive enough warmth to support liquid water. TRAPPIST-1's entire 7-planet system fits within a region roughly the size of Mercury's orbit around our Sun. But red dwarfs, despite their faintness, tend to be dramatically more magnetically active than Sun-like stars, prone to frequent intense flares and bursts of high-energy radiation. A planet orbiting close enough to stay warm ends up sitting directly in the blast radius of that activity, absorbing far more damaging radiation over its lifetime than a planet at a more comfortable distance ever would. Over billions of years, that radiation can gradually strip a planet's atmosphere away entirely, a process researchers have been modeling and worrying about for years, now increasingly confirmed by direct observation rather than theory alone. This matters well beyond TRAPPIST-1 itself, and that's precisely why the results have landed so heavily in the exoplanet science community. Red dwarfs make up roughly 3/4 of all stars in the Milky Way. If planets orbiting close enough to these stars to stay warm are also, as a general rule, orbiting close enough to have their atmospheres stripped away by stellar activity, it doesn't just affect one system. It potentially rules out habitability for a significant fraction of all the rocky planets in the entire galaxy, the ones we're statistically most likely to actually find and study, given how common red dwarf stars are compared to Sun-like ones. That statistical weight is exactly why this particular finding stings more than a typical null result. Astronomers didn't choose to study red dwarf systems like TRAPPIST-1 out of convenience alone. They chose them because if planets around these stars turned out to be habitable, the sheer abundance of red dwarfs across the galaxy would mean vastly more potentially livable worlds exist than a universe built primarily around rarer, Sun-like stars could ever offer. A negative result here carries outsized statistical weight precisely because of how common the underlying star type is. It's the difference between ruling out one unusual, rare category of planet and potentially ruling out the default environment most rocky planets in the galaxy actually experience. Not everyone considers the story finished, and it genuinely isn't. TRAPPIST-1's outer 3 planets, F, G, and H, sit farther from the star's most intense flares and haven't yet been studied with the same level of scrutiny as the inner 4. Researchers involved in this work have been careful to note that all hope isn't lost, particularly for these more distant, colder worlds, which may have had a better chance of holding on to water and other atmospheric components precisely because they've spent less time directly in the path of their star's worst outbursts. Additional Webb observations are already scheduled, including 15 further transits of TRAPPIST-1, paired specifically with repeated observations of the confirmed airless planet B, using its already known bare rock spectrum as a calibration tool to better separate genuine atmospheric signals from the star's own contaminating noise. Astronomers researching this system have described their work as detective work that's only just beginning, not a case that's already closed. Even so, the direction of the evidence gathered so far is difficult to spin as good news. What Webb has detected in the TRAPPIST-1 system isn't a dramatic single event or a shocking one-time signal. It's a slow, mounting, planet-by-planet pattern, confirmed independently by multiple research teams using different instruments and different techniques, all pointing toward the same uncomfortable possibility, that the galaxy's most common type of star may make it genuinely difficult for nearby rocky planets to hold onto the atmospheres life as we understand it actually requires. Upcoming missions, including the European Space Agency's Plato mission launching this year and its follow-up Ariel mission planned for later this decade, are being built in part specifically to widen the search beyond TRAPPIST-1, testing whether the same pattern holds true across other red dwarf systems scattered throughout the galaxy. If you want to be here when Webb finally tests the outer TRAPPIST-1 planets and settles whether any real hope remains for this system, subscribe and turn on notifications, because whatever the telescope finds next at 40 light years away, this remains one of the most closely watched answers in the entire search for a second Earth.